welcome Dr. James Glazier. Today he is our guest. Please, James, go ahead and introduce yourself and your research laboratory. Tell more what your research is about, what its mission, and what is your vision.
Well, I'm a professor of intelligent systems engineering at Indiana University, and my area of research is in computational bioengineering. And my goal is to take medicine from being a reactive field where we wait for problems to happen, then try treatment. Engineering systems, we have control as our fundamental operating principle. We don't wait for problems to happen. We predict them, we prevent them. Medicine is one of the few areas which is not designed in the way human engineered systems are designed. And to me, the failure to be able to prevent disease and to be able to intervene before there are catastrophic failures in medicine is a great target of where we should be going in 21st century engineering and medicine. If we are going to control things, we need to be able to understand them and predict them. And so the focus of my research is on building mechanistic predictive models of complex biological systems and also enabling others to do that by building software infrastructure, open source software infrastructure that enables that kind of modeling to be done. I also am heavily involved in community building. I'm a co-leader of a working group for IMAG-MSM, which is sponsored by the National Institutes of Health, which has the goal of understanding the human immune system to allow better control of the immune system in infectious diseases.
Thank you so much. Essentially, technologies do you use? How do you build the projects? What do you build them upon?
So my own work has two arms, as I mentioned. We build software platforms that are classical, in a sense, classical high-performance computing, scientific and engineering modeling software. So we build software that allows people to develop sophisticated computer simulations of cells and tissues. And so that's one hat that I wear. The other hat that I wear is actually building models of specific disease systems using that software. Before COVID, I also had a wet lab, but everything shut down in COVID, and I haven't reopened the wet lab since COVID. And so these days, my work is almost entirely computational. I collaborate with experimentalists around the world. We work with regulators as well. We work with the U.S. Environmental Protection Agency in their research on toxicants. And so our typical mode of action is to work closely with experimental and clinical groups to develop computer simulations of particular diseases or particular conditions, and then often try to either to understand the basic science of those, whether it's not understood, or to help improve therapies where those things are understood.
Yes, it is very powerful to combine the experimental biology with theoretical, since biology is very complex and computation often helps to solve those problems which can't be solved sometimes experimentally. What had been your biggest achievements to date in this area?
Well, the software platform that we developed, which is called CompuCell, is the most widely used software in this field. I should say, to be honest, it's not a very big field. It's a new field, so it's not like Microsoft Office where you have billions of users there. But in our world, it's significant. We've worked in areas in particular related to vascular disruption and kidney dysfunction. And so we have done modeling of a disease called autosomal dominant polycystic kidney disease, which is a relatively rare but nevertheless significant genetic condition that leads to overgrowth and cystic formation in the kidneys, which is currently treatable only by kidney transplant. So most people die waiting for a kidney transplant. And the simulations we did in conjunction with Dr. Robert Bacallao at the Indiana School of Medicine, who's a surgeon specializing in this, suggested new avenues for drug therapy. And we're currently trying to get those drugs into clinical trial to see whether we could come up with drug treatments for this lethal disease. We've worked quite a bit in the area of vascular disruption, in particular trying to understand the basic mechanisms of diabetic retinopathy, age-related macular degeneration, and suggest improved approaches to therapies for those. Those are a little bit further from turning into medical applications. In the context of infectious diseases, we've built platforms that allow people to explore drug dosing schedules, for example. I'd also say that even though it's not the work that we did, it's work using our platforms, the work that's been done by the Environmental Protection Agency in understanding developmental toxicology, trying to understand how particular drugs can lead to birth defects, using our software tools has been very impressive. They've worked in the area of cleft palate in particular, and estrogen mimic disruption of genital development. And I think that the work that they've done on top of our platform has been really important.
Yeah, thank you so much for this. This is really amazing to see such big progress. What do you wish for your research laboratory? What is your vision? What do you like to achieve? And what are your current goals?
Well, the things that I would like to work on now would be to expand into digital twin more generally. Prediction is necessary to build digital twins, but it's not the only thing that you need. You need to couple the predictive models to sensor technology. You need to be able to do rapid parameter estimation. You need to be able to evaluate many treatment strategies. And ultimately, you need to be able to deliver the treatments that are proposed by those systems. That kind of closed loop system isn't something that can be done by one lab or even one cluster of labs. Developing true immune digital twins, for example, would be a project that would require hundreds of groups to work together. And we've been working recently on trying to set up an umbrella organization that would promote that kind of collaborative and international research effort to develop the ability to control the immune system, whether that's when you're suffering from COVID-19, in cancer, which is also a disease of immune failure, arthritis, which is a disease of immune failure. And so to be able to actually understand the functioning of the immune system, which is extremely complex, predict it, and then ultimately be able to control it.
It is a very big goal, and having such a big goal, of course, this is very beneficial because this is what moves you forward, that what drives you, that what keeps you up at night. And this is something that's very important. What would you say to those who are listening right now and they are students, they are bachelor, they are master student, maybe they are PhD students, or maybe they are already scientists. We also have those who are probably investors, some are angel investors, some are big VC companies. What message would you send to them?
Well, everyone knows today that artificial intelligence is important. And students are going into artificial intelligence and data science. But it's a bit of a dirty secret that artificial intelligence can only work on data sets that exist. And so you can't train on things that have not happened if you're going from real world data. And so the kind of mechanistic simulations that I do and that the people I work with do are essential even if you're using AI systems because they give you the ability to explore things that don't exist in the real world, what are called counterfactuals. And I think the way forward will be in the union of machine learning, artificial intelligence techniques with predictive mechanistic models. When they work together, they're much more powerful. And I think what we need, if I were a venture capitalist, what I would say is that we need some killer applications. I would say immune control is one. I would say understanding the cornea and damage to the cornea is another. It seems very different, but there are a lot of related problems. We're working with Procter & Gamble Corporation on corneal modeling at the moment. And I'd say to students, so I think there are real opportunities there. I think in 5 years, we're going to see medicine change in very fundamental ways. For students, I would say that you might think about understanding biology more. When I talk to companies that are hiring, they really think that they could teach people computing, but they can't teach people to appreciate biology. And so understanding biology is really hard and really important. And I think that with the rush to AI, mechanistic modeling has been a little bit overlooked. But when I look at the students who graduate from my lab and related labs, they're hired with straight PhDs, hired by pharmaceutical companies at salaries that are higher than a full professor's salary. There's a tremendous shortage of people with training in biology and modeling together. And there's a huge opportunity if you're interested in building companies, going to work for large pharma companies. There are wonderful companies like Nova Discovery in Lyon, France. It's doing virtual clinical trials. HeartFlow in Palo Alto, California, that's doing diagnostics that are based not on our platform, but on related kinds of approaches, mechanistic models, that are going to transform medicine as we know it. And I think that those are tremendous opportunities for students going forward if they're willing to learn this combination of medicine, biology, computing, and of course some machine learning too.
Sure. Thank you so much for this. This is, of course, a difficult question. These are big disciplines, but combination of the knowledge in these disciplines brings the highest value which we can achieve for treatment of the diseases and for alleviation of the hard outcomes, even if we are talking about the side effects of the existing known drugs. Good. Thank you so much for this. Would you have anything else to add besides that what we already spoke?
Well, I'd say that the future is just getting started. If you look at the use of these kinds of techniques in biomedicine, there are very few cases. There are a couple. The real digital twins that are used now are very simple. They exist in pacemakers, have simple digital twins in them, and what are called artificial pancreas, implanted insulin pumps with sensors, have very simple digital twin models. CPAP breathing machines have simple models of the way the patient breathes. But I think we're only beginning to be at the dawn of the world where we're going to be able to combine sensor technology, predictive modeling, and actuators to revolutionize medicine. And so I'm very positive about this. I think it's a great time to be going into the field, whether as a student or as an investor.
Thank you so much. Thank you.